Every branch of math has what they call a fundamental theorem. There is a fundamental theorem of arithmetic. Okay, the fundamental theorem of arithmetic is that everything that you do can be undone. In other words, if you add, you can subtract. If you multiply, you can divide. If you raise to a power, you can unraise to a power with a radical. Everything, that's the fundamental theorem of arithmetic. Everything you do can be undone. Same thing with, there's a fundamental theorem of algebra. But it's the same thing. Everything you do can be undone. So in algebra, we do stuff to both sides. If we've got an e on one side, we do an ln. That undoes it. If we have a square, we do a square root. If we have a sine, we do a sine inverse. Everything can be undone. That's the fundamental theorem of algebra. Geometry too. The fundamental theorem of calculus is the same. Everything you do can be undone. If you can do a derivative, then what can you also do? An antiderivative. Okay, everything you do can be undone. All right, so that is the fundamental theorem. We just got to put it down into words. All right, you're not going to find this explanation in your book. These are my own words. All right, you can undo a derivative with an integral. That's what we've been working on. But the converse of that is true. So what would the converse statement be? You can undo an integral, which is the same thing. Okay, you can undo an integral with a derivative. Okay, that is the fundamental theorem. In both cases, you must remember the chain rule. It is that statement right there, that third statement, remembering the chain rule, that is the most challenging thing to remember, especially when it comes to a multiple choice option, because the people who forget the chain rule, that option is going to be there and they will gladly and happily choose it. Those who remember the chain rule will make actually the right choice. So here's how you write it in like math script. That's sort of the English explanation of it. Here's how you write it in math script. If you have an integral and it's going from a to b of f of x dx, it is possible to undo that integral if you take the derivative. The way we show that is using our friend Leibniz, and he would do this. Take the derivative, d whatever, of whatever comes next. Okay, the derivative of the integral. And what will you be left with when you take the derivative of an integral? And the answer is this. You will be left with just f, not capital F, because you've undone it. With which bound plugged in first? B. And then here's where the trick part is. Almost, I would say 50% of the time people forget the chain rule. Not only when you do this do you have to plug in the top bound of B, but you also have to multiply by the chain rule of B prime. Then you subtract, and then you'll plug in the lower bound of A, but you also have to remember to multiply by the chain rule of A prime. Notice that we're not using capitals anymore. Okay, capitals would be for if we were just doing the integral, but we are doing the integral with a derivative. And so the integral with a derivative cancel each other out, and you're just basically, I mean, think of it this way. It's like these two things cancel out, and all you're left with is f, but you do have to plug the bounds in. This is what's called the fundamental theorem of calculus, and we're just going to practice taking the derivative of an integral, so canceling out an integral with several different examples. This does not have, for today, there's not going to be practical applications of it. It's just going to be one of those straight homework assignments that's all functions and numbers and stuff. All right, so the example, find each derivative. And I'm just going to give you 1, 2, 3. Let's start with 3 of those. Okay, example A. Y equals the integral from 2 to 2x cubed of sine of t of dt. And we want to find the derivative of each of those. So y is defined as an integral, and we want to undo that. We want to find the derivative. So y prime would be the derivative on the left side, and then we need d dx applied to the integral on the right side. So the answer to that would be y prime equals. The derivative symbol cancels out the integral symbol, so those are canceled out, but I have to plug in my bounds. And so this would become sine with the upper bound plugged in of 2x cubed and multiplied by the chain rule of 2x cubed, which we know to be what? 6x squared. Minus sine of the lower bound plugged in multiplied by the chain rule of the lower bound, which in this case is what? 0. And so the final answer is 6x squared in front of sine 2x cubed, and then the 0 wipes out the whole second half. So that is the derivative. Okay. The derivative cancels out the integral, but not the bounds. Oh, let's try another one. Okay, h equals the integral from a to 2a of 1 over 1 plus t squared dt. Notice how the variables are irrelevant right now. Okay, the variables are irrelevant. I can use y's, I can use x's, I can use whatever. All right, if we're going to find the derivative of this, it would be h prime equals. Now d what? Okay, the derivative with respect to a. Okay, it's the variable that's part of the bounds, not the variable that's part of the function. So d dA of the a to 2a of the function 1 over 1 plus t squared dt. So again, the integral and the derivative cancel each other out, but they don't cancel out the bounds. And so when the bounds get substituted in, I will have 1 over 1 plus the upper bound of 2a substituted in squared. So 2a takes the place of t. But I also need to remember to multiply that by the chain rule of what the derivative of 2a was, which is 2. Minus, and the lower bound will be 1 over 1 plus a plugged in for t. And then multiplied by the chain rule of the lower bound, which is 1. The dt in the question is your reminder, okay? It's like you're not substituting in just for this part, but you got to substitute in for the dt part as well. That's the differential. So that's the part, that's the chain rule part. It's both. And then we can clean this up. So my h prime is going to be 2 over 1 plus 4a squared minus 1 over 1 plus a squared. You don't need to find a common denominator. It's fine if you just leave it expressed like that. Sometimes a common denominator would be worse. Yeah? dt is like your reminder right here. Like after the expression, the 1 over 1 plus t squared, there has to be a dt part. dt represents the differential. That's the chain rule part. Okay? All right. Let's do C. Okay, r equals the integral of 2x to 5 of the expression 1 over t dt. Okay, my dr d what equals d what? All right, so dr d, and then if this is with respect to the variable that's part of the bounds, which is going to be x. And that will be applied to the integral from 2x to 5 of 1 over t dt. So the derivative notation cancels out the integral notation but does not cancel out the bounds. So dr dx equals 1 over 5 times the chain rule of 5, which is 0, minus 1 over 2x times the chain rule of 2x, which is 2. Now the 0 is going to wipe out the 1/5. The 2's will reduce each other, and I'm left with negative 1 over x as my derivative. Okay, any questions on that so far? Okay, all right, let's try this. All right, solve for f of x. Here's your question. If the integral goes from 5 to x on f of t dt, and if that's equal to x squared plus sine 2x, and the directions are solve for f. Well, where is f right now? On what side? Where do you see it? On the left side. What else is on the left side besides f? An integral. So in order for me to solve for f, I have to get rid of the integral. In order for me to get rid of the integral, I've got to use a derivative. So I'm going to use d dx applied to get rid of the integral. But if I do it on the left side, I have to do it on the right side as well. So you need to apply the derivative rules correctly. There's a derivative rule on the left for how to deal with an integral, and there's separate derivative rules on the right. On the left side, the derivative cancels out the integral but not the bounds. So I will be left with x with the bound, f with the bound of x plugged in times the chain rule of 1, minus f with the bound of 5 plugged in times the chain rule of 0. On the right side, I just used regular derivative rules. So the derivative of x squared is 2x. The derivative of sine is cosine. And the chain rule on 2x is 2. So you apply the appropriate derivative rules to each piece, and then you clean it up. So f of 5 times 0 will be gone. And so f of x by itself is 2x plus 2 cos 2x. And I just solved for f of x. Yeah?
If it was integral plus 2x and then f of x.
Right, they need to be, yeah, that does not work. Okay. All right, so this is, I think the last one we'll be able to fit in. I wanted to do one more. Shoot, we just probably have to wait till Monday when everybody else gets here. All right, find a tangent line. At x equals 1 to the equation y equals 2x to 5 of 1 over t dt. All right, this is kind of a blast to the past. What do we need to have to find a tangent line? What, two things? A slope and the point. All right, so to find the point and the slope, to find the point, we're going to plug 1 into y. To find the slope, where are we going to plug 1 into? into y prime. Okay, to find the point, you plug 1 into y. To find the slope, you plug 1 into y prime. Well, plugging 1 into y is right there. So when I plug 1 into y, I will have 2 times 1 over 1 over t dt. And I can just do that like normal. Just evaluate 1 over t dt is the natural log of absolute value of t plus c evaluated from 2 to 5. And I'm just going to do that like normal, and I'll finish it up. To plug into y prime, I'm going to have to do d dx first to figure out what y prime is on the 2x to 5, 1 over t dt. And so then, okay, this derivative cancels out that, but not the bounds. And we actually did this problem just in the letter C previously, so we can scroll up. I already showed it to you. And it turned out to be 1 over x. Right, was that the one? Yep, 1 over x, negative 1 over x. So this is negative 1 over x, and I'm plugging 1 into that. So I get negative 1 when you plug 1 in. So that's how you get your point and your slope. And then you write the tangent line using our tangent line formula that we had from before Christmas. Okay, so you'll plug your point and your slope into that.